The concept of the Big Bang has shaped our understanding of the universe, laying the foundation for modern cosmology. Based on Einstein's theory and what is recognized as standard cosmology, the Big Bang was the moment when the cosmos began its expansion, marking the creation of all matter, energy, space, and time. This occurrence happened approximately 13.8 billion years ago and brought about the vast universe we observe today. However, recent developments in cosmology suggest that the Big Bang might not be the absolute origin. Instead, there may have been a phase before the Big Bang that was equally influential in shaping the universe as we know it. This earlier period is referred to as cosmic inflation. Inflation is one of the most captivating features of present-day cosmology. It proposes that before the hot, dense state of the Big Bang, the universe underwent a remarkably rapid exponential growth. During this time, the universe was doubling in size at an astounding speed. To demonstrate how extreme this expansion was, if the universe started smaller than an atom, it would have expanded to be far larger than the entire observable universe within a fraction of a second, about a millionth of a second. This stage of growth didn't last long, but it played a crucial part in shaping the universe. When inflation ended, the energy driving this expansion was released into space, warming it up and forming the particles of matter that compose everything we see in the universe. In many ways, inflation is the forerunner to what we currently call the Big Bang. While the theory of inflation is widely accepted in cosmology today, there are still many unresolved questions. For instance, we do not yet comprehend what caused inflation in the first place, what caused it to stop, or how long it lasted. These are open questions in cosmology, and solving them is crucial for a deeper understanding of the universe's origins. Before inflation, the universe was an incredibly dense, tiny point of matter, often called a singularity. From this singularity, the expansion began and eventually led to the creation of atoms, molecules, stars, and galaxies. The idea of the Big Bang as the beginning of everything is appealing, but modern cosmology suggests a more complex picture. Some theories suggest that the universe underwent a period before the Big Bang. During this time, inflation caused the universe to expand exponentially, doubling in size at least 80 times in an instant. This rapid growth was fueled by an unidentified form of energy that permeated empty space. When inflation ended, the energy that had driven this expansion was converted into particles, heating the universe and resulting in the hot, dense state we refer to as the Big Bang. This inflationary stage was cold and void, but it established the foundation for the creation of matter and the universe we observe today. One of the more speculative ideas in modern cosmology is the theory of eternal inflation. This hypothesis suggests that inflation didn't stop everywhere at the same time. Instead, it ceased in different regions, creating many separate zones or bubbles, each of which could be a universe in its own right. Our universe would be just one of these patches. According to eternal inflation, there could be an infinite number of these universes, each with its own set of physical laws and constants. The idea of the multiverse enters here, the idea that our universe could be one of many, or even an infinite number of universes. If this theory is true, it may explain why life is perfectly suited to our universe. In this multiverse scenario, every possible combination of physical laws could exist in different universes. We just happen to live in one where the conditions are just right for stars to form and for elements like carbon, oxygen, and others necessary for life to emerge. Although theories like eternal inflation and the multiverse remain speculative, the idea of inflation itself is backed up by actual evidence. The strongest evidence for inflation comes from the cosmic microwave background, CMB, radiation that is the earliest known light in the universe. The CMB was emitted around 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This light offers clues about the universe's earliest moments, helping researchers understand what happened just after the Big Bang and providing support for the inflationary theory. One of the most important findings came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images show slight variations in the temperature of the early universe, and these variations match the predictions made by inflationary theory. This experimental evidence strengthens the idea that inflation is not just a speculative theory but a key element in our understanding of the cosmos. Understanding the Big Bang and what came before it requires combining two of the most significant theories in modern physics: quantum mechanics and general relativity. General relativity explains the large-scale structure of the universe, such as the behavior of galaxies, stars, and planets. Quantum theory, on the other hand, explains the behavior of matter at the smallest scales. To answer the ultimate questions in cosmology, such as what space and time are, and where the universe came from, scientists need to develop a theory that combines these two frameworks. If these frameworks were successfully unified, they would allow us to understand not only the Big Bang but also the conditions that led to it. One of the more unexpected characteristics of the universe is its size. The farthest objects we can observe are about 47 billion light-years away, meaning the observable universe is roughly 94 billion light-years across. This may seem paradoxical given that the universe only dates back 13.8 billion years. How can the observable universe be larger than the distance light could travel in the age of the universe? The answer lies in the fact that the universe has been expanding throughout its history. As the universe grows, the distance between objects increases, making far-off objects farther than the time that light would take to reach us. Most scientists believe that the universe extends far beyond what we can observe. In fact, it's quite possible that the entire universe is infinite. The observable universe is simply the part we can detect, limited by how far light has been able to travel since the Big Bang. There may be vast regions of the universe that we will never be able to see. The question remains, is there anything beyond the universe? Most scientists are skeptical about this notion. If the universe is infinite, there is no beyond, it would just continue forever. Even if the universe is finite, it might not make sense to talk about anything beyond it. Space and time are properties of the universe as a whole, and the concept of beyond the universe may not have any physical meaning. Just as the beginning of the universe is a topic of intense study, so too is its eventual end. The best current estimate is that the universe will continue to expand forever. This is due to a mysterious force called dark energy, which is causing the universe's expansion to accelerate. As to what caused inflation and what caused it to stop, these remain some of the deepest open questions in theoretical physics. Several hypotheses have been proposed, such as the existence of a scalar field, often referred to as the inflaton field, whose dynamics could have driven the rapid expansion. According to this idea, the energy stored in the inflaton field caused space itself to expand, and as the field decayed, its energy was converted into particles and radiation, triggering the conditions we associate with the traditional Big Bang. However, the true nature of the inflaton field remains unknown. Is it a fundamental part of our universe, or is it an emergent property of something even deeper? Some theories suggest that the inflaton might be tied to quantum gravity, a framework that would unify quantum mechanics and general relativity into a single coherent theory. Others explore the possibility that inflation is a recurring phenomenon in a cyclical universe, where expansion and contraction alternate indefinitely. Another challenge in understanding inflation is that it occurred at energy levels far beyond what we can reproduce in any experiment on Earth. While particle accelerators like the Large Hadron Collider allow us to probe high energies, they are still many orders of magnitude below the energy scales relevant to inflation. This makes direct tests of inflationary models extremely difficult, leaving cosmologists to rely on indirect evidence, like the cosmic microwave background and the distribution of large-scale cosmic structures. Despite these challenges, progress is being made. Next-generation telescopes and satellite missions, such as NASA's upcoming Light BIRD mission and proposed observatories like the CMBS-4, aim to detect even subtler imprints of inflation in the polarization of the CMB. If detected, these signals, called B-mode polarization patterns, would provide powerful new confirmation of the inflationary paradigm and potentially reveal information about the inflaton field itself. In the broader scope of cosmology, the unanswered questions about inflation point to a more fundamental mystery. What is the origin of the laws of physics themselves? Why do constants like the speed of light, Planck's constant, or the strength of gravity have the values they do? If the multiverse is real, it may imply that these constants vary across different universes, and we simply inhabit one in which the conditions are right for life, a principle known as the anthropic principle. Still, many scientists are unsatisfied with anthropic reasoning and hope for a deeper, more predictive theory, one that explains why inflation happened, why it stopped, and why our universe took the shape it did. Ultimately, the story of the universe, from the initial expansion, through cosmic inflation, the birth of matter, the formation of stars and galaxies, and toward a possible frozen, desolate future, reveals not just how far science has come, but also how many mysteries still lie ahead. Every discovery brings new questions, and each question leads us closer to understanding the origin, structure, and fate of everything that exists. What lies beyond the universe that can be observed? Is there a multiverse? And if so, how many other universes are there? As scientists continue to investigate the universe with advanced technology and theories that combine quantum mechanics with general relativity, we will undoubtedly learn more information about these enigmas. The search to understand the universe is ongoing, and each discovery brings us closer to answering the ultimate question of our existence. Exploring the origins and structure of the universe is not only a scientific endeavor but also raises philosophical questions about existence, reality, and our place in the cosmos. One of the key areas in cosmology is understanding dark matter, which is thought to make up about 27% of the universe's mass-energy content. Unlike normal matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is important for describing the formation and dynamics of galaxies. Recent experiments and observations have revealed more about dark matter's properties, but its exact nature remains elusive. Various candidates have been proposed, including massive, weakly interacting particles, WIMPs, and actions, but no direct evidence of dark matter particles has been found yet. The search continues through a combination of ground-based experiments, astronomical observations, and simulations that model how dark matter affects the large-scale structure of the universe. Yet another important part of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up approximately 68% of the universe's mass-energy content. Its discovery was unexpected, and it has led to many theories, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is vital, as it will determine the universe's ultimate fate. Scientists are examining how dark energy affects cosmic structures and attempting to comprehend whether it remains constant over time or evolves. Alongside dark matter and dark energy, the study of cosmic structure formation also provides valuable insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and matter clumping together under the influence of gravity, have demonstrated the formation of complex structures. Supercomputer simulations aid scientists in understanding how these structures developed over billions of years and continue to evolve. Astrobiology intersects with cosmology too, as researchers aim to understand the conditions that support life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has accelerated, with thousands discovered in recent years. Some of these stars contain exoplanets in habitable zones, where liquid water could exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and what it might look like. Additionally, the role of fundamental physics in cosmology is essential. The search for a unified theory that combines general relativity and quantum mechanics continues to challenge physicists. Theories like string theory and loop quantum gravity aim to merge these two domains, offering potential explanations for phenomena like black holes and the early universe. As technology advances, our ability to observe and interpret cosmic phenomena improves. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe by providing unprecedented detail of distant galaxies and cosmic events. With each new observation, we are gradually piecing together the puzzle of the universe's creation, evolution, and ultimate fate. In conclusion, the study of the universe contains an abundance of scientific exploration and philosophical inquiry. From the fundamental forces that shape cosmic structures to the search for extraterrestrial life, our quest for knowledge reflects humanity's deep curiosity about the cosmos. As we work to answer these profound questions, we not only gain new insights but also develop a deeper appreciation for the vastness and complexity of the universe. The relationship between observation and theory is crucial in cosmology. Innovations in technology, such as advanced detectors and machine learning algorithms, are improving our ability to analyze astronomical data. These tools enable researchers to sift through vast amounts of information, identifying patterns that could reveal new insights into cosmic phenomena. One important area of investigation is gravitational waves, ripples in spacetime caused by catastrophic events like colliding black holes or neutron stars. The finding of these waves has opened a new avenue for studying the universe. Through observation of gravitational waves, scientists can gain insights into the nature of these extreme events and test theories of gravity in ways that traditional methods cannot. The concept of cosmic time is also intriguing. Unlike our everyday perception of time, which is linear and uniform, cosmic time is shaped by the expansion of the universe. This raises questions about the nature of time itself. Is it an absolute concept, or does it depend on the observer's position and motion? These philosophical questions parallel scientific exploration, highlighting the variety of aspects of cosmological research. The formation of the first stars and galaxies, known as the cosmic dawn, is another critical area of focus. Understanding this epoch helps explain how the universe transitioned from a hot, dense state to the complex structures we see today. Observations of high redshift galaxies provide clues about the processes that occurred during this pivotal time, supporting scientists in constructing a timeline of cosmic evolution. Another essential component of cosmological research is the cosmic microwave background, CMB, the faint glow left over from the Big Bang. This radiation provides a snapshot of the early universe approximately 380,000 years after its origin, offering critical insights into its initial conditions, composition, and rate of expansion. High-precision measurements of the CMB, such as those conducted by the Planck satellite, have helped refine our models of the universe and test predictions made by inflationary theory. Inflation theory proposes that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. This rapid growth explains several observed features of the universe, such as its large-scale uniformity and the absence of magnetic monopoles. Although indirect evidence supports the theory of inflation, scientists are still searching for direct signals, such as specific patterns in the polarization of the CMB, that could confirm or rule out different inflationary models. In tandem with these theoretical pursuits, observational cosmology continues to evolve. Large-scale surveys of the universe, such as the Sloan Digital Sky Survey, SDSS, and the upcoming Euclid and Vera C. Rubin Observatory missions, aim to map billions of galaxies across cosmic time. These efforts help reveal the structure, expansion history, and distribution of matter in the universe on the grandest scales. Beyond mapping, these surveys also assist in understanding cosmic acceleration and testing the foundations of general relativity itself. For example, by comparing how galaxies move with how they cluster, researchers can test whether gravity behaves as expected or if alternative theories are needed. Meanwhile, particle physics and cosmology remain tightly linked. The conditions of the early universe are a natural laboratory for testing high-energy physics theories. Experiments at the Large Hadron Collider, LHC, and future particle accelerators may help explain why matter prevailed over antimatter, a question known as the baryon asymmetry problem, and whether unknown particles played a role in cosmic evolution. Equally compelling is the growing interest in the multiverse hypothesis, which suggests that our universe might be just one of many. Some versions of inflation theory, particularly eternal inflation, predict a vast ensemble of universes with varying physical constants, dimensions, and laws of nature. While this idea is still speculative and difficult to test, it represents a bold frontier in theoretical physics and forces scientists and philosophers alike to reconsider the uniqueness and fine-tuning of our cosmos. The possibility of a cyclic universe is also being explored, where the universe undergoes endless cycles of expansion and contraction. These models challenge the traditional view of a singular beginning and end, proposing instead a perpetual rhythm governed by quantum or gravitational effects. Finally, cosmology is increasingly interdisciplinary, merging insights from astronomy, physics, mathematics, computer science, and even philosophy. Machine learning is now commonly used to process astronomical data, simulate galaxy formation, and identify gravitational lenses. Quantum computing, though still emerging, promises to accelerate complex simulations that would be otherwise impossible with classical methods. In sum, the study of the cosmos is not static, it is a dynamic, ever-evolving endeavor shaped by the synergy of theory, observation, and technology. As we probe the mysteries of dark matter and dark energy, gravitational waves, cosmic inflation, and the possibility of parallel universes, we also deepen our understanding of ourselves, our origins, our future, and our place in the grand cosmic story.